everyone, Manny here, and welcome. Last time, we looked at infinite limits. In this lesson, we will be taking a look at limits at infinity. In other words, we will be taking a look at the limit as x approaches infinity of a function. Okay, we're going to first determine the relationship between limits at infinity and horizontal asymptotes. Recall that horizontal asymptotes are the lines which a function is approaching as x approaches infinity. So if you have, say, a function like this, as x approaches infinity, this function is continuously approaching this function, this horizontal asymptote, call it y equals L, as x approaches infinity. As x grows and grows, this function is growing as well, but it is getting as close as possible to y equals L without actually getting there, without actually touching it. And that is a horizontal asymptote. So a horizontal asymptote is present at y equals L if the following limits are true. So you can either approach it from as x approaches infinity, or you can do it from negative infinity. So you can also have a graph that approaches y equals L when x approaches negative infinity. In either case, you have a horizontal asymptote. Okay, so let's discuss some important properties that we'll need for this lesson. So the first property is the limit as x approaches positive or negative infinity of a fraction. So this fraction consists of a numerator that is a constant, say 3, and x raised to any power. So this power is a positive number that is also rational. So it could be a half power, it could be to the third power, second power, as long as it's a positive and rational number. So let's say x squared. And this property says that this limit will become 0. Why is that? Well, note that if you're going to take the limit of this, you're going to take the limit of the numerator divided by the limit of the denominator. And the limit of the numerator is just going to be 3. And then you're going to take the limit of the denominator, which is x squared. So you're going to make x bigger and bigger. So when you make the denominator bigger and bigger, recall what that does to the fraction. The fraction gets smaller and smaller as the denominator grows bigger. So if it was 3 over 1, that's 3. 3 over 2, 1.5. 3 over 3, 1. 3 over 4, 0.75, and so on. And the fraction goes down until it dwindles to 0 at infinity. Now the second property is taking the limit at infinity for a polynomial, a general nth order polynomial term. And this states that the limit at infinity for a nth order polynomial is just solely given by the limit of the leading term. That is the term that has the leading coefficient and the variable raised to the highest power. And the reason for that is that the highest power, the degree of a polynomial, is what determines the end behavior of the function. So recall how to determine end behavior. So if the degree of the polynomial is, say, even, so if n is even, and say the leading coefficient is positive, then the end behavior is upwards. As x approaches negative infinity, the function goes up, and as x approaches positive infinity, the function goes up, sort of like a parabola. And if n is even, but the leading coefficient is negative, then your tails are going to go both down. And if n is odd, if the highest power is odd, then and the leading coefficient is positive, then the function is going to go down as x approaches negative infinity, but up as x approaches positive infinity. And the case will be opposite if it was negative. So it would go up first, then down. So in the same way, this property helps you determine end behavior. So what happens as x grows bigger and bigger on both sides? What happens to the function? How does it behave? And this is essentially end behavior. Okay, so the last property that we're going to cover is as a radical property. It's not a property that's related to limits at infinity, but it's a property that I wanted to remind you of because we're going to need it in one or two of the examples later on in this lesson. So it says that if you're taking the nth root of x to the n, that you can't just call it x. It's going to be absolute value of x if the index is even, and it's going to be x if the n is odd. So the reason why is that if you're taking an even root of a number, you can only output a positive number from it. You can never get a negative number for it, and you can't take the root of a negative number. So, for example, if we're taking the square root of -3 squared, so notice that the index and the power are the same. So we're just going to say that this is square root of 9, which is going to be 3. So you can't just cancel these out and say that that's going to be -3, right? That's not correct. You can't output a negative number from this. You have to say that it's square root of 9, and then square root of 9 is 3, right? And that only happens if this is an even root. It doesn't matter if it was an odd root. So if you had the cube root of -3 to the third, notice that it doesn't matter if you cancel it out and get -3, or if you did -27, and then the cube root of -27 is -3. See, that doesn't give you any problems. So therefore, what we do to rectify the even roots is by saying that it's equal to the magnitude or the absolute value of the number. That way, if it's negative and we cancel out, and we end up canceling out, then we can just take the absolute value of the number and just take the positive part of it. Okay, the first example. So basically, what you have to do for these limits, this is a polynomial limit. Remember that we said that one of the properties was that it's based on the leading term, right? The term with the highest power. So we should be able to take the limit as x approaches infinity of just the leading term with the leading coefficient, and that should give us our answer. So note that if we just plug in, quote unquote, plug in infinity into this, infinity squared, infinity times infinity, remember that's one of our properties, that's equal to infinity. And then remember also that a number L times infinity will still give us infinity. So this is infinity. Another way that you can look at this, and which basically proves the property, is as follows. So what you can do is factor out the highest power, right? So you're going to get x squared times 2 minus 7 over x plus 5 over x squared. Okay, so now if you plug in infinity into these denominators here, remember the denominator is going to get bigger and bigger, and you have a constant in the numerator, so that means this is going to go down to 0. And then similarly for the x squared term, this is going to go to 0, one of our properties. When you plug in infinity here, that leads you to where we started. And this is essentially why end behavior only depends on the highest power, is because of this. The other terms dwindle down, and it's only based ultimately on the leading term. So in this way, you get infinity. Now, what happens if we didn't do this? What happens if we just plugged in infinity right away? Well, what you're going to do, let's figure out what we get. So we're going to do 2, and we'll just say plug in infinity, infinity here for every x we see, right? Infinity squared, we said that's infinity. Infinity times 2 is infinity. Now, remember, if you have a negative number times infinity, that's gonna turn it to negative infinity. And then you have your plus 5. So negative infinity plus 5 is just negative infinity. Doesn't really mess with your answer. So you have infinity minus infinity. Remember that this is one of those, from the previous lesson, this is one of those indeterminate forms. Because you're not sure if this belongs to 0, right? Or if it belongs to the case where it's negative infinity, that is where this infinity over is bigger than this infinity, or whether it belongs to the other case where this infinity is bigger than the second one, in which case we get infinity. In our case, this infinity ultimately won out, and you were left with positive infinity. And I showed you how to find that. But this is what would happen if you were to plug it in directly without using any of the properties. You would be stuck because you would get an indeterminate form. Okay, so for part B, we have the limit of another polynomial here. And just, I want to show you the factor form again so that you can get practice with that. And then we'll, of course, use the property, the shortcut property. So our highest power is R3. So we're going to factor out x to the third from this whole polynomial. Okay, so you're going to get 8 over x to the third. Remember, when you're factoring, you're just basically dividing here. So, and then you're left with 1 over 2, and you have an x left over, minus 1/3. Okay, so if you plug in negative infinity into this term, it becomes 0. Into this term, it becomes 0. And then if you plug in infinity into this, you're going to get negative infinity to the third power times negative 1/3. Okay, so negative infinity to the third power, that's going to be a negative number, right? So you're going to get negative infinity. And negative infinity times negative 1/3 is positive infinity. So this is going to be positive infinity. Okay, for the last example, we're going to get, okay, so in order to deal with rational functions, what you have to do is look at the highest power in the denominator. Okay, so the highest power in the denominator is x squared. So what we're going to do is divide the top and bottom by that x squared. So this is what you do if you have a fraction and you're taking the limit as x approaches infinity. Look at the denominator and find the highest power, then divide by it. So I'm going to divide by my highest power of my denominator. Okay, and then take the limit, of course. Then you're going to distribute. So you're going to get 3x squared over x squared minus 2x over x squared, and so on. So you're going to get 3 for the first part minus 2 over x minus 1 over x squared over 1 minus 5 over x squared. Okay, then you take the limit. So if you take the limit of this of 3, that's just going to be 3. If you make the denominator of this grow bigger and bigger, this is going to dwindle to 0. Same for this, it's going to dwindle to 0. This is going to stay 1. This is going to dwindle to 0. And you're left with 3 minus 0 over 1 minus 0, which is just 3. And that's how you deal with these. Remember, if you plugged it in, you're going to get, if you plugged in infinity directly without doing this step, you're going to get an infinity minus infinity term, and that's going to be indeterminate. You're not going to be able to determine what that's going to be. And then you're going to get that over an infinity term, which will be worse. Okay, so remember we talked about horizontal asymptotes. So this wants us to find them. Determine if there are any horizontal asymptotes of these following functions using limits and algebra. Okay, so remember from algebra, when we determined horizontal asymptotes, there were 3, maybe 4 cases. So let's talk about those cases right away. So the first case is if the degree of the numerator, and we're going to call that d, the degree of the numerator was less than the degree of the denominator. Okay? Denominator and numerator. So if the degree or the highest power of the numerator is less than the highest power in the denominator, then we have a horizontal asymptote at y equals 0. The second case was if the degree of the numerator was equal to the degree of the denominator. Then we said that we had a horizontal asymptote at y equals the leading coefficient number of the numerator. Let me erase this. Leading coefficient of numerator divided by leading coefficient of denominator. So it was the ratio of the leading coefficient of the numerator to denominator. And the third the third case was if the highest power in the numerator was greater. And you can divide this into another subcase, which I think I will. Then you have a horizontal asymptote. Well, it states that you have no horizontal asymptote. So let's say you have no horizontal asymptote. The subcase is that if this is greater by 1, then you have an oblique asymptote. You have an oblique asymptote. So you may or may not remember this from your algebra class. And we can show that this is the case using the limits at infinity. So in this case, for part A, we know that we should get a value of 0 because the degree of the numerator is less than the degree of the denominator. The degree of the numerator here is 0 because it's to the 0 power. There's no x here. And the degree of the denominator is 1. So therefore, we fall into the first case. So this should equal to 0. For part B, the degree of the numerator is less than the degree of the denominator. Should also give us 0. For part C, same case. And you can just apply this to rational functions with polynomials. You won't be able to necessarily apply this to part D. For part E, the degree of the numerator is greater than denominator, so it should fall under no horizontal asymptote. Okay, so we're going to show this right now. So let's show this using the limits at infinity. So limit as x approaches infinity of 1 over x minus 4. So remember when you have a fraction, right, with when you have a rational function, you take the highest power in the denominator and divide everything by it. So divide by x, divide by x, divide by x. Okay? So that gives you 1 over x over 1 minus 4 over x. So remember, the denominator of this gets bigger and bigger. This goes to 0. This goes to 0. Leaves you with 0 over 1, which is 0. Which is indeed what we said it would be. Now the next case, limit as x approaches infinity. So the highest power denominator is is 2, so we're going to divide by x squared, divide by x squared, divide by x squared. So that leaves us with negative 1 over x over 1 minus 9 over x squared. And then if you plug in infinity here, remember that goes to 0, that goes to 0, leaves us with 0 over 1, which is 0. This one here, same process, divide by x squared, divide by x squared, divide by x squared, divide that by x squared. Leaves you with 1 over x minus 5 over x squared, 1 minus 7 over x squared, or 7 over x, plus 10 over x squared. So this is 0, this is 0, 0, 0, leaves you with 0 over 1, or 0. Now, technically we're supposed to do this at infinity and negative infinity, but it doesn't matter if you do negative infinity in a, b, or c. It does not matter if you plug in the limit as x approaches negative infinity or positive infinity. The numbers still dwindle, the fractions here still dwindle down to 0. So you're still going to get 0 for those answers. Now for part D, we're going to make sure to do both limits at infinity, the positive version and the negative version. So let's do that. Okay, so you're going to have e to the negative infinity over infinity. Okay, remember what this is. Remember what the negative exponent tells you. The negative exponent tells you that you're going to flip the position of the exponent, of the exponential function, right? So this is going to go flip down to the denominator. Okay, so we have 1 over infinity, and then we have e to the infinity. Okay, e to the infinity is just infinity, because the e gets bigger and bigger. So we have 1 over infinity times infinity. Remember we said infinity times infinity is just infinity. And 1 over infinity, remember a constant over infinity is 0. So this limit is 0. Okay, so we have a horizontal asymptote at y equals 0. And let's do the other side just to be safe. If you plug in negative infinity, that gives you e to the negative infinity, which becomes positive infinity over negative infinity. E to the positive infinity is infinity. Infinity over negative infinity. This is an indeterminate form. This is one of the properties that we saw in the previous section when we talked about properties of infinity. We cannot determine what the value of infinity over negative infinity is. Does it belong to the case where it's negative 1? Or does it belong to the case where the numerator is bigger and you get infinity? Or does it belong to the case where the denominator is bigger and this is 0? We cannot determine this. So this is an indeterminate form. Okay, we won't figure out how to determine these kinds of limits where you have indeterminate forms of infinity over infinity until the next chapter. So we won't cover it in this lesson or even in this chapter. Okay, so again, we're going to do the same process here. So we're going to look at the highest power in the denominator. So divide this whole thing by x squared and divide this whole numerator by x squared. Okay, 1 by 1, right? So you're left with limit x approaches infinity of x minus 2 over x plus 3 over x squared divided by 1 minus 5 over x minus 1 over x squared. Okay, again, if you plug in infinity into this, this becomes 0, 0, 0, and 0. It leaves you with limit as x approaches infinity of x. Okay, so let's write that out. which is simply going to be infinity. You're going to plug it in and you're going to get infinity. So what this is telling you is that the function increases without bound as x approaches positive infinity. As x gets bigger and bigger, the function y gets bigger and bigger, right? So this is saying that it has no horizontal asymptote, which is what we were saying. If the degree of the numerator is greater than the degree of the denominator, you have no horizontal asymptote. Okay, so for the last part, we have here limit x approaches infinity. Oh, and by the way, if you did negative infinity for part E, you're still going to get the same answer. You're still going to get, let's do that real quick before I forget. So if we do negative infinity, we're going to get limit as x approaches negative infinity of x, right? When everything else cancels out and becomes 0. And this is going to give you negative infinity. Okay, so again, even if you approach from negative infinity, you're going to get negative infinity and you're not going to get any horizontal asymptotes. So you would say none for the horizontal asymptotes. Okay, so let's go back to part F. So we're going to do both infinity and positive infinity. Again, the limit of a product is the product of the limits, okay? So the limit of 5 is just 5. The limit of this, you can just think of it as doing the limit of the exponent, right? So we can just go ahead and do a direct substitution. So 5 times 2 to the, and normally you would do a direct substitution, but remember what I was saying, that this is a polynomial, right? So you can just look at the highest power and that will tell you what the limit is. So we're going to look at the highest, the leading coefficient, which in this case is x squared. So we're just going to say infinity squared and just call it a day for the rest of the polynomial. So we have 5 times 2 to the infinity. 2 to the infinity is infinity. 5 times infinity is infinity. Okay, if we did the limit as x approaches negative infinity, then again we have 5 for that part, 2, and then again you're going to only look at the highest power, so you're going to get negative infinity squared. And then negative infinity squared is just positive infinity, which leads you to the same answer that we had before, infinity. So in this case, there are no horizontal asymptotes. Okay, so we're going to do the same thing here, just different functions. So the first example, we have a radical. Okay, so when you have radicals, you're still going to do the same, you're still going to look at the same process. Okay, so you're going to divide by, basically you're going to just divide by the highest power in the denominator. Usually that's what you do, right? You divide by the highest power in the denominator. But in this case, since you have a radical, we're just going to pull out that x squared there. Okay, so we're going to pull out that x squared, factor it out, leaves us with 1 plus 4 over x squared. And there's a reason why we're doing this. You're going to see. Okay, now we have to do the square root of x squared, right? Normally you'd be able to pull this out as an x, right? Be careful. When you have the radical, the index matching this, and it's an even root, you're doing a square root, so that's an even root, you're not going to pull this out as an x. You're going to pull it out as an absolute value of x. Because based on the property that I was mentioning earlier, if you have the nth root of x to the n, that's going to give you absolute value of x if n is even, which it is in this case. This is important because it's going to impact your answer. So we have absolute value of x, and then we are left with square root 1 plus 4 over x squared all over 1 minus 2x. So we're going to divide everything here. Remember, we're going to look at the denominator and divide it by the highest power, which is x. So we're going to do 1 over x minus 2. We're just going to divide it. And we need to divide this numerator by x as well. Okay? Which we just did. Okay. Then we're going to go ahead and plug in our infinity. When we plug in infinity here, this is going to go to 0. When you plug in infinity here, that's going to go to 0. So we're left with the limit of this term here, and then over the negative 2. So we got to figure out what the limit of that term is. So let me rewrite this as negative 1/2, okay, because this is 1 over negative 2 here, which we can pull out. Okay, so negative 1/2 limit x approaches infinity of absolute value of x over x. Okay, remember that the absolute value is a piecewise function. Absolute value of x equals x when x is greater than 0 and negative x when x is less than 0. So in this case, if we're taking the limit as x approaches infinity, it's safe to say that we're looking at positive numbers, right? So we can take the first case and say that absolute value of x is simply x. So here we're left with, this becomes x, and then x divided by x cancels, leaving you with 1. 1 times negative 1/2 is negative 1/2. Okay, so we have one horizontal asymptote at x equals negative 1/2. So we're going to say we have a horizontal asymptote at not x, at y. Horizontal asymptote at y equals negative 1/2. Now let's do the other side. Let's do, that's for this. Now we're going to do the limit as x approaches negative infinity and see what we get. Again, I'm not going to redo the work. The work is the same. You're going to factor out the x squared, and you're going to get absolute value of x. So you're going to be left with the same term that we had before. The only difference is now that you're doing negative infinity, you're looking at the case where absolute value of x equals negative x, because that's when x is less than 0. Since you're doing negative infinity, you're doing negative numbers, so you're looking at this case. So you're going to replace x here with negative x. Negative x divided by x is negative 1. So this leaves you with negative 1 times negative 1/2, which is positive 1/2. So therefore, you also have a horizontal asymptote at y equals positive 1/2. That is for part A. Okay, so for part B, we look at that. We don't have any radicals, so we don't have to pull out anything out of the radical. We just have a basic fraction with polynomials. So we're just going to pull out whatever the highest power is in the denominator, or divide it off, same thing. So we're going to divide by t to the third. So divided by t to the third, divided by t to the third. Okay, so limit t approaches infinity. So you're going to get 3t squared divided by t cubed, which is just 3 over t. T to the 6th divided by t to the third is t to the third. Then you have 1 over t to the third minus 5. Okay, so this is going to give you 0. Then you're going to have infinity to the third, which is just infinity, right? This is going to go to 0. So you're going to have infinity divided by negative 5, which is going to give you negative infinity. Okay, so that's for t approaches positive infinity. Okay, then we're going to look at the negative infinity version, which is still going to give us, the 3 over t t to the third. That doesn't change. This is still going to become 0, 0. Now you have negative infinity to the third is negative infinity. And over negative 5, negative infinity divided by negative 5 is positive infinity. So in essence, you don't have any horizontal asymptotes for this one. So you would say no horizontal asymptotes. Okay, so we're going to look at the third example now. So we have a radical in the bottom, and it's in the denominator. So what we're going to do is we're going to try to find the highest power that we can divide off, or that we can factor off. So it doesn't really matter. We can divide it off or factor it out. So let's just try factoring so that you can get in the habit of it and you can get used to it. So remember, the degree of the denominator is technically x squared, because it's technically x to the square root of x to the fourth, which is x squared. So we're gonna pull out an x squared, or divide it off from the top and bottom, however way you want to look at it. So yeah, we pull it out from the top, we get 1 plus 3 over x squared. Then we're gonna remember, when we pull out of an x squared from the bottom, it's gonna pull out as an x to the fourth. Okay, and then the square root of x to the fourth is x squared. So this becomes x squared. And then these pull out, these cancel. Now remember that this you don't have to worry about the radical property that we talked about, because the index does not match the power here. So you don't have to worry about writing absolute value or anything for this case. Okay, so in this case, this just cancels out, no problems. And then we're going to take the limit as x approaches infinity. In that case, this becomes 0. This becomes 0. This becomes 0. And you're left with, this should be times. So you're left with 1 plus 0 divided by the square root of 1, which is simply 1. Okay, in the same way, if you plugged in negative infinity, you're going to get the exact same answer. And the reason why is because you don't have any absolute value properties that may change the answer to, say, -1 or anything like that. Everything is going to remain the same. Everything is going to become 0 until you're left with 1 over 1. So if you did the limit as x approaches negative infinity, I'm going to call this f of x, it's still going to be positive 1. So you're going to have a horizontal asymptote at y equals 1. Okay, so for part D, we have another radical here. And there's several ways that you can do it. Okay, so we're going to do limit as x approaches infinity. Now what we can do is we can just divide by the highest power in the denominator, just like we've been doing. Remember that when we divide by x, which is the highest power, when we divide by x, that's the same thing as dividing by x squared on this numerator, on this square root of x part. Okay, so it's the same thing, because if you divide, so here, if you divide by x, so if you do this, 1 over x, and you bring it in the radical, it becomes x squared, right? So you just got to be careful with that. So when we divide that and this, okay, so this becomes 1, this becomes 0, 0, that becomes 1, and this becomes 1 over x, right? So let's write it out. And then if we plug in infinity there, that's going to become 0, okay? So you're left with 0 over 1, which is 0. Okay, what happens if we do the limit as x approaches negative infinity? Well, the answer is going to be undefined, or does not exist. We're just going to say it does not exist because you cannot let x become negative infinity, and you can't let x be negative inside a square root. So it's going to be a does not exist. So therefore, we only have a horizontal asymptote at y equals 0. Okay, now we're going to do the last part of this example. Okay, so for now we're just going to plug in infinity and see what we get. So we get e to the 10 times infinity, which is e to the infinity. E to the 6 times infinity, which is infinity. And we get negative infinity. Remember that this is going to become 0 because this is the same thing as 5 over e to the infinity. And e to the infinity is infinity, so you get 5 over infinity, which is 0. So this part goes to 0. The problem parts are these, because these give us an indeterminate form. This is going to give us infinity minus infinity, right? So that's the part that we're obviously going to have to try to deal with. So what we're going to do is factor out the largest power out of these two, okay? So the largest power is clearly going to be e to the 10x. So we're going to factor that out of just these two. This is not going to be a problem because it's going to go to 0. So let's do that. So e to the 10x times, and we get 1 minus 2e to the negative 4x. And then we have minus 5e to the negative 12x. Okay, so this is going to go to 0, like we said. And now this is going to go to 0. And we're simply going to have infinity times 1, which is its infinity, minus 0, which is infinity. So our limit is infinity. Now we're going to do the limit as x approaches negative infinity. Okay, so note that if we plug in negative infinity in here, we're going to have e to the negative infinity, which is going to go to 0. So that's not going to be a problem at all. We plug it in here, we're going to get 0 as well. Okay, we plug it in here, we're going to get e to the positive infinity, which is infinity. So this is perfectly fine because if these go to 0, then you're going to be left with just an infinity term, right? You're not going to be left with any indeterminate forms, so you don't have to do any factoring out whatsoever. Okay, so in this case, we're going to have 0 minus 0 because of these two terms, and then minus 5e to the infinity because negative infinity times negative 12 is positive infinity. E to the infinity is simply infinity, and then negative 5 times infinity is going to be negative infinity. So we're left with negative infinity. Okay, to summarize this lesson, we talked about notation for limits at infinity, which we did indirectly by doing the examples as well as talking about the relationship between horizontal asymptotes and limits at infinity. Remember that limits at infinity are to horizontal asymptotes as infinite limits is to vertical asymptotes. We also talked about some important properties for limits at infinity, as well as that one property for radicals, where the nth root of x to the n is absolute value of x, or x, depending on whether when n was even or odd, right? In addition, we talked about limits at infinity for polynomials. Remember, for polynomials, you just want to look at the end behavior. which is basically looking at the leading coefficient term, and that will tell you what the limit at infinity would be. For radicals, the trick for radicals that when you factor out and use this property, if you need to, or you just factor out like normal and proceed. We also did some rational functions, some fractions, where we look at the denominator and we pull out the highest power in the denominator, or we divide numerator and denominator by the highest power of the denominator. And we also did some examples with exponential functions. I do hope that you found this helpful, and this is going to be the last section of this chapter. The next chapter will be focused on derivatives.